Hello dear students, Assalamu alaikum. I hope you will be fine. My name is Engineer Mir Masood Shah. I am lecturer in Department of Technology, Sarhad University of Science and Information Technology, Peshawar. As I am teaching you the subject Fluid Mechanics, today is your lecture number 7. In lecture number 7, we will study about rate of discharge, equation of continuity, and different types of flow. So first of all, we will study about rate of discharge. So what is rate of discharge? The quantity of a liquid flowing per second through a section of a pipe or a channel is known as the rate of discharge, or simply discharge. So the quantity of liquid flowing per second through any section is known as discharge. It is generally denoted by Q. Now consider a liquid flowing through a pipe. Let A is equal to cross-sectional area of the pipe and V is equal to average velocity of the liquid. So discharge Q is equal to area into average velocity, which is equal to Q is equal to AV. Now note, if the area is in square meter and velocity is meter per second, then the discharge Q is equal to cubic meter per second, which is equal to Q max. Also remember that 1 cubic meter is equal to 1000 liter of water, or in 1 cubic meter there are 1000 liters of water. Next is equation of continuity of a liquid flow. If an incompressible liquid is continuously flowing through a pipe or a channel whose cross-sectional area may or may not be constant, the quantity of liquid passing per second is the same at all the sections, and this is known as the equation of the continuity of a liquid flow. It is the first and fundamental equation of flow. Now, to prove the equation of continuity, consider a tapering pipe through which some liquid is flowing, as shown in figure 6.1. This is a tapering pipe through some liquid is flowing. At 1,1 the diameter of the pipe is different than the diameter of the pipe at 2,2, and also at 3,3 all the diameters at different points are different, so the pipe is tapering. In actual practice, here it is a note, in actual practice the velocity of a liquid is maximum at the center. The velocity of a liquid is maximum at the center of the pipe and is minimum near the walls, and this is because of the friction between the walls and the liquids. For all calculation in hydraulics, the average velocity of flow at the section is taken. Now let A1 is equal to cross-sectional area of the pipe at section 1,1 and V1 is equal to velocity of the liquid at section 1,1. Similarly, A2, V2 is equal to corresponding values at section 2,2, and A3, V3 is equal to corresponding values at section 3,3. Now we know that the total quantity of liquid passing through section 1,1 is equal to Q1 is equal to A1 V1, and let that is equation 1. Similarly, the total quantity of liquid passing through section 2,2 is Q2 is equal to A2 V2, and this is equation 3, while the total quantity of liquid passing through section 3,3 Q3 is equal to A3 V3, and let this is equation 3. Now from the law of conservation of matter, we know that the total quantity of liquid passing through the section 1,1, 2,2 and 3,3 is the same. So therefore Q1 is equal to Q2 is equal to Q3, and that is equal to equal to so on, or A1 V1 is equal to A2 V2 is equal to A3 V3, and so on. So this is the equation of final equation of continuity. Now we will solve some example on this equation of continuity. As we have example 6.1. The statement of the problem is or example is the water is flowing through a pipe of 100 mm diameter with an average velocity of 10 meter per second. Determine the rate of discharge of the water in liters per second. Also determine the velocity of water at the other end of the pipe if the diameter of the pipe is gradually changed to 200 mm. So initially water is flowing through a pipe of 100 mm diameter and the average velocity of flow is given, which is 10 meter per second. We have to find the rate of discharge of the water in liters per second. Also we have to determine the velocity of water at the other end of the pipe if the diameter of the pipe is changed from 100 to 200 mm. Now first of all, in solution we will write the given data. In given data we have d1 diameter 1 is equal to 100 mm given, which is equal to 0.1 meter. Divide 100 by 1000 as 1 meter is equal to 1000 mm. So we will get the 100 mm in meters. So divide 100 by 1000, we will get 0.1 meter. V1 is also given, which is equal to 10 meter per second, and D2 is also given, which is 200 equal to 0.2 meter. Now first of all we have to find rate of discharge. So for that purpose we will find first of all we find the cross-sectional area of the pipe. So we know that the cross-sectional area of the pipe at point 1, A1 is equal to pi by 4d square. As the pipe is circular, so use the area of circle, which is pi by 4d square. So d1 value is already given, which is 0.1. So put the value of d1 and we will get the area A1 is equal to 7.854 into 10 to the power 3, 10 to the power minus 3 square meter. So this is the area of the pipe at point 1. Now to find the rate of discharge, we have equation Q is equal to A1 V1. A1 is already find out and V1 is already given, so put the values. A1 is equal to 7.854 into 10 to the power minus 3, while V1 is equal to 10 meters per second. So putting the values, we will get the rate of discharge, which is equal to 78.54 into 10 to the power minus 3 cubic meter per second. Now we have to find the discharge in liter per second. So multiply this value by 1000, as 1 cubic meter is equal to 1000 liters of water. So multiply this by 1000 and we will get the rate of discharge in liter, which is equal liters per second, which is equal to 78.54 liters per second. And this is the answer of the first part. Now we have to find the velocity at the other end of the pipe. So finding the velocity of the pipe at the other end of the pipe, we also know that the cross-sectional area of the pipe at point 2, A2 is equal to pi by 4 into D2 square. D2 value is already given, so put the value of D2, you will find the you will get the area of the pipe at point 2, which is A2 is equal to 31.42 into 10 to the power minus 3 square meter. Now to find the velocity of water at point 2, we have equation Q is equal to AV. Clear? So we have to find V. So V2 is equal to Q divided by A2. As discharge value is already found out, so use this value and divide this value by area A2. You will get the velocity at point 2, which is equal to 2.5 meter per second. And this is the answer of our part 2, which is velocity of the liquid flow at point 2. Next we have example 6.2. The statement of the problem is a pipe AB branches into two pipes C and D as shown in figure 6.2. This is the pipe AB, which is branching in two pipes BC and BD. The pipe has a diameter of 0.45 meter at A, 0.3 meter at B, 0.2 meter at C, and 0.15 meter at D. Find the discharge at A if the velocity of water at A is 2 meters per second. Also find out the velocities at B and D if velocity at C is 4 meters per second. So we have to find the discharge at A if the velocity of flow, velocity of water is at A is 2 meters per second. The diameter of the pipe at different points is given. At A it is 0.45 meter, at B it is 0.3 meter, at C it is 0.2 meter, while at D it is 0.15 meter. Also we have to find the velocities at B and D if the velocity at C is 4 meter per second. So first of all, in solution we will write the given data. In given data we have dA is given, it is diameter at point A equal to 0.45 meter. Also dB is equal to 0.3 meter, DC is equal to 0.2 meter, and dt is equal to 0.15 meter. Also velocity at point A, VA is equal to given 2 meter per second, and VC, which is velocity at point C, is given, which is equal to 4 meter per second. Now first of all we will find the discharge at point A. So we know that the cross-sectional area of the pipe at point A is equal to pi by 4dA square. The A value is already given, which is 0.45. So put the value, you will get the area at point A, which is AA is equal to 0.159 square meter. Now we have to find the discharge at point A. So we have equation of discharge Q is equal to AB. Area of the pipe at point A is already found out, which is 0.159, and VA is already given, which is 2 meter per second. So put the value, you will get the value of discharge at point A, which is equal to 0.318 cubic meter per second. Now we have to find the velocity at point B. We know that the cross-sectional area of the pipe at B is equal to pi by 4 dB square. dB value is already given, which is 0.3. So we will get the area of AB, which is equal to 0.0707 cubic square meter. Now we have to find the velocity at B. So VB is equal to Q divided by AB, as the original equation of discharge is Q is equal to AB. So from this right equation we will find the velocity which come out to be V is equal to Q divided by AB. So putting the value of discharge from the above answer, which is 0.318 cubic meter per second, and AB is already find out, which is 0.0707. So we will get the velocity at point B, which is equal to 4.5 meter per second. Now we have to find the velocity at D. For that we have to, first of all we have to find the cross-sectional area of the pipe at point C. So AC is equal to pi by 4 DC square. DC is already given 0.2, so we will get the area of AC, which is equal to 0.0314 square meter. Now the discharge at D, to find the discharge at D, QC is equal to AC VC. So AC is already find out and VC is already given. So put the value, you will get the value of QC, which is discharge at point C, which is equal to 0.1256 cubic meter per second. And now to find the discharge at D, we have QD is equal to QA minus QC. So as you can see in the figure, the total discharge in the figure at this point is equal to discharge at point A, as this pipe is same. Now at this point, some quantity of water will move on this in this pipe, and some quantity of liquid or water will move in this pipe. So we have already find out the discharge in this pipe, which is BC pipe. So we will minus this discharge from this discharge, and we will get the remaining discharge which moves in this pipe. So that is equal to QD is equal to QA minus QC. QA is already found out, which is 0.318, while and QC is already found out, which is 0.1256. So we will get the discharge at point in pipe D or point D, which is QD is equal to 0.1924 cubic meter per second. Now we also know that the cross-sectional area at pipe at D, AD is equal to pi by 4 dt. dt is already given, which is 0.15. So AD, which is area at point D, is equal to 0.0177 square meter. Now using this area and QD, we will find the velocity at point D, which is equal to VD is equal to QD divided by AD is equal to 0.1924 divided by 0.0177. So we will get the velocity at point D is equal to 10.9 meter per second, and this is the answer of our example 6.2. The next topic we have types of flow in a pipe. So when a liquid is flowing in a pipe, the innumerable small particles get together and form a flowing stream. These particles, while moving, group themselves in a variety of ways. For example, they may move in a regular formation, just like as a disciplined soldiers do, or they may spiral or jostle like the individual in a disorderly mob. The type of flow for liquid depends upon the manner in which the particles unite and move. Though there are many types of flow, yet the following are important from the subject point of view. So the first one is uniform flow. Flow is in which the velocity of liquid particle at all the sections of a pipe or channel are equal. Then this type of flow is known as uniform flow. This term is generally applied to flow in channels. The next type of flow is a non-uniform flow. So a flow is said to be non-uniform in which if the velocity of liquid particles at all sections of a pipe or channel are not equal. So this type of flow, when the velocities of liquid particles at all the sections are not equal, is known as a non-uniform flow. The next type is a streamline flow. So a flow in which each liquid particle has a definite path and the path of individual particles do not cross each other. So this type of flow is known as a streamline flow, and it is also called as a laminar flow. The other type of flow is a turbulent flow. A turbulent flow in which each liquid particle does not have a definite path and the path of individual particle also cross each other. Then this type of flow is known as a turbulent flow. The next one is a steady flow. A flow in which the quantity of liquid flowing per second is constant, means the rate of discharge is constant. Then this type of flow is said to be a steady flow. A steady flow may be uniform or non-uniform. The other one is unsteady flow. So a flow in which the quantity of liquid flowing per second is not constant, means the discharge is not constant. Then this type of flow is said to be an unsteady flow. And this is the end of our today's lecture.